Welcome back to ECE 442-542. Exam number 1 is coming up shortly. Too much feedback. Oh well, seems to be okay now. Maybe I was just too charged up. Or maybe it was where I was standing. All right, onward. Homework number 2 is due on Thursday of this week. Exam number 1 is on Wednesday of next week. And we may or may not have a live review session depending on the votes. And I might or might not influence that voting process or interpretation of that voting process. I don't know. We'll see. But maybe we might have it in this room right after the lecture next Monday, if that's what the votes indicate. I don't think anyone comes in here. They don't right at 7, so we'll see how that goes. Hopefully that makes sense as it's being passed around. The goals for today, one is simply to get us thinking about what we're doing and we'll continue to do today. And the first thing that we'll start with is simply to write down and compare and contrast continuous time and discrete time exponential damped responses or exponentially damped responses. And we'll look at their pole zero patterns in the two different planes, the S plane and the Z plane, depending on whether it's continuous or discrete. We will then derive the Z-transform of exponentially damped cosine, and then on a homework problem, you have to derive the exponentially damped sine, and that should just be a straightforward repeat with a slight variation on homework problem maybe number 4, on homework set number 2. We'll simply state some Z-transform properties. Those should not come as any surprise if you're comfortable with the Laplace transform. Then we will look very quickly at the frequency response of h of z. And where is our stability boundary in the Z-plane? Right on the unit circle. Where's the stability boundary in the S-plane? Well, this boundary is right on the imaginary axis, right? And if we wanted the frequency response in the continuous time, we were evaluating that transfer function as we walked up the imaginary axis. We're evaluating g of s at points of j omega. We're replacing s with j omega. That says we're restricting our attention to the imaginary axis. For the frequency domain, we're actually restricting our, now we're walking around the unit circle. We don't have to walk as far. So you don't have to be quite as in shape as you were in the continuous time case. Now you just have to go partway around that unit circle, right? Go from 1 to -1. -1 sometimes can be viewed as infinite frequency. We'll look at that later. But that's what I'm trying to illustrate here, that we are looking at h of z when we replace z with this particular curve right on the boundary of the unit circle. That's when z is equal to e to the j omega t, which is found. We know that z is equal to e to the st. Now we can look at what s, or what happens when we replace s with the imaginary axis. That now translates into h replacing z everywhere with this e to the j omega t. Now it looks a little ugly, but we could actually do that graphically also in the Z-plane like we've done for the continuous time case. And if we get there, we will talk a little bit more about the region of convergence. But I hope after class someone came forward and said, what about this region of convergence and inside the unit circle? It's really two different things. The region of convergence is not the same as stability. So you can have an unstable system, which is illustrated here. Last time we said, okay, if we have a signal or a waveform that's a discrete time waveform, and it's collapsing or decaying or growing with r, with this ratio r at each time interval, then we derived its Z-transform to be Z over Z minus R. That result is true whether R is less than 1 or bigger than 1. It didn't matter. The region of convergence is always outside of that, and that allows your Z to make this product of RZ collapse, and that's why it's called the region of convergence, so that that sum is bounded. Meaning this R could be 0.5, it could be 5. This is still okay, Z over Z minus 1/2, or Z over Z minus 5. It's just the region of convergence is different. For the unstable case, which is if little r was 5, you would be growing at each time step by a factor of 5. It would be 1 to start with, let's say, if we didn't scale it. Then it would be 5, 25, and it's growing quite quickly. But it still has a Z-transform. Just like, and this is the pole zero pattern in the Z-plane, which isn't shown very well. I get in trouble when I do this before class when I'm not hooked up to this poorly less resolution projector. Okay. I'm restricted by the resolution of the display device, and when I'm just on my lap before class, I can have a nice little display. When I hook it up to that guy, it's not quite as nice. That's why that happens. All right, I don't do it on purpose, I just forget. The continuous time case, remember that for the Laplace. If we have e to the at, an a can be either negative or positive, and that then corresponds to something that collapses, decays, or it builds or grows with time. In the S-plane, and your Laplace transform is 1 over S minus A. You're used to seeing 1 over S plus something. Well, that's because you might have written this as e to the minus 2t. And now you have this exponential decay, and that gives you a Laplace transform of 1 over S plus 2, which gives you a pole over here at minus 2. I'm drawing this or sketching this for an A value that's positive. But you still have, well, we never really talked too much about the region of convergence, but if your S is basically bigger than that A is, you're multiplying by e to the minus st. That S is going to allow that argument of your integral to be giving you a bounded result in the Laplace transform. So we may not have talked too much about the region of convergence, but you still get this 1 over S, let's say, minus A if A is positive. And you simply have a pole at the A value, whether A is positive or negative. That's the continuous time, and I want you to start getting comfortable with these ideas. What you're maybe very comfortable with in the continuous time setting or the Laplace case, and gaining that same comfort level for the discrete time case. What if we make this a little bit more interesting and we now have an exponentially damped sinusoid, cosine or sine? That's meaning we have something that's oscillating with a damped frequency, and it's also collapsing, let's say, if the exponential is negative. So we now have this damping oscillation as an initial condition response. Let's look at what we have, or just remind ourselves of that behavior for the continuous time case. Now I'm going to let sigma be positive so that I do have a decay, e to the minus sigma t. Do you remember what its Laplace transform equals in terms of sigma and omega sub d? Pardon? So we have a complex set of poles, don't we? And they have a real part of minus sigma, and they're away from the real axis plus and minus j omega sub d. It's sometimes the numerator that gets a little bit forgetful, but that's s plus sigma. So we have a 0 at minus sigma, and we have poles at s plus sigma squared plus omega sub d squared. Meaning if we were sketching this, the pole zero diagram associated with that exponentially damped cosine waveform in the S-plane we now have these two poles that are minus sigma into the left half plane. And they are away from the real axis, a vertical distance of plus and minus j omega sub d. And we also have that 0 right there at minus sigma. And that's now what the pole zero diagram looks like for this exponentially damped cosine waveform in the time domain, or in the continuous time setting. We want to find the discrete time analog, or the similar kind of response for a discrete time system. What does that look like as far as x of n might be concerned? A lot of times we can gain good insight if we simply replace t with a sampled version of t. Let's say little n, capital T, where capital T is the sample period. But before we do that, we want to express x of t, because this is going to be more straightforward to apply the discrete, or the Z-transform to, is let's now rewrite this using Euler. Do you remember Euler? Euler's your friend. Well, maybe not in real time, but I don't know, maybe there's an Euler walking around, maybe he's, but not this Euler. I don't think he's walking around anymore. He's deceased. But what I want to do is write that cosine as two complex exponentials, or the sum of two complex exponentials. And now I can actually clean that up a little bit by distributing that e to the minus sigma t. Or let me keep that negative with the sigma. And if we wanted to, we might refer to this as some frequency or S variable S1, and there's S sub 2. So if you let S1 equal this guy and S2 equal that guy, that puts you in a certain point in the complex S plane, if that's how you want to think about it. Now let's replace little t with a sampled form of that. So that now we have x of t evaluated where t is equal to nt. And what we can try to keep track of is what's sort of fixed and what's a function of time. Capital T is fixed once we pick the sample period. Sigma is fixed once we know the decay amount. And omega sub d is fixed once we've determined or been given the damped frequency of oscillation. The time variable is that lowercase n. So let's factor that out and put everything else together. And we could, well, let me do that first. So this is now 1/2 e to the minus sigma nt e to the j omega sub d nt now let me pull the n out of the common term on both of those, and I now have e to the j omega sub dt to the n plus e to the minus j omega sub dt to the n. And I might, I'm getting writer's cramp, so let me just call that theta sub d. And this now is also, you can think of that as an angle, theta sub d. Which, if I do that, do you see that this is now e to the j theta sub d n plus e to the minus j theta sub d n? But that should look familiar to you. That's just 2 times the cosine of theta sub d n. Using Euler again, we have 1/2 or the 2's cancel. My hand came back alive, and now we have cosine omega sub dt theta, or cosine of theta sub dt, and sometimes we might just write that as some ratio r. E to the minus sigma t is just a number. That's r to the n cosine of omega sub dt n. And that's now our time domain expression for an exponentially damped cosine. Here's the damping, the r, for a negative or a positive sigma. E to the minus sigma t is going to give us some number that's less than 1. And this cosine of theta sub d n tells us basically how many times we're going to sample or see that waveform in each cycle of this oscillating waveform. meaning here comes my art class disaster again, but this is now time, and we could view this we could obtain this collapsing envelope, e to the minus sigma t, and we also have this cosine that's getting collapsed by this decaying or exponential decay. And if we sample at a certain frequency, we now are going to be seeing something like that. That's now our exponentially damped cosine waveform. How quickly it decays is dependent on the size of R and how many oscillations we have in a unit time is going to depend on that theta sub d. And we want to know, if we have this waveform, what's its Z-transform look like? And now that we have it expressed as this amplitude, or this radial or ratio R, and this oscillating piece, which we can think of that oscillating piece as, in terms of Euler, these exponentials, that's going to make our algebra easier when we start looking at this infinite sum. Let's now Z-transform this time domain waveform. So all we've done so far is rewritten and obtained a exponentially damped cosine. And you can do this for an exponentially damped sine wave for the homework. Now what we want to do is Z-transform. Our x of n is now then 1/2 r to the n e to the j theta sub dn plus e to the minus j theta sub dn. Just expanding that cosine of theta sub dn. This is, again, so I'm going to be going back and forth with notation, but this is now the r to the n, and then the cosine is e to the theta dn plus e to the j theta dn plus e to the minus j theta sub dn over 2. That's where this 1/2 comes from now in my x sub n, or x of n. And now we can apply the Z-transform. It's only one-sided. Our sum then needs to only worry about the positively indexed values of n from 0 to infinity. But now we need to introduce that x of n. But that now gets scaled by z to the minus n, where this piece is our x of n. Well, we can actually separate that out into two pieces. This sum is a linear operation, so that now we can write that as 1/2 sum plus another sum. And what we want to do is identify a ratio that each of those terms in that infinite sum vary by. Or I could now say that that's an r e to the j, whoops. You guys need to keep me awake. That n should have been on the theta sub d's, right? You let me drop it when I went to the Z-transform. Don't drop it during an exam or during your homework. I can drop it because I can change it, but and not get too much grief for it. Well, you can give me as much grief, but it's not going to harm my grade. All right, so are we back on a more accurate representation of the Z-transform of this exponentially damped cosine? Now I don't want it in there. Why don't I just call those two different pieces, an x sub 1 and an x sub 2? Yes. Did I not? Yes, I did drop a negative sign. I'm just making sure you guys are with me here. Is that okay? Yeah, this is late in the day. Huh? Can't use that excuse either on an exam. So don't try. Now we have capital X of Z is 1/2 summation x sub 1 to the n and x sub 2 of n. And do you remember what that ends up being when we apply our strategy for finding these infinite sums? What can I replace that infinite sum with? One over 1 minus x1, right? Remember where that comes from? Do I need to remind us? Yes, no? Better put my eyes back on. Yes, no? We're good on that? Just look at it and then compare the sums, and you know when those converge. But this now says that x of z is now equal to, if I, and I hope you appreciate why I'm calling that x1 and x2, so I don't drop all those minus signs and thetas, etc. This is now 1/2 1 minus x2 and if we do the algebra, we end up with 1/2 and 1/2. That gives us 1 upstairs, and we now have 1/2 of x1 and x2 with a minus sign. And downstairs, we have the product of 1 minus x1 and 1 minus x2. And you probably won't see that in a Z-transform table, because they won't have changed these notations and created an x1 and an x2. So let's go back and remind ourselves of what we had. x1, well, we're going to have to find that product. x1 was r e to the j theta sub d z to the minus 1. X sub 2 what's that give us? I'll do the easy part. R squared, right? Then we have these complex exponentials combined, which give us an exponent of theta d minus theta d, or 0. So that's e to the 0, that's 1. And we have z to the minus 2. So now, even all that ugly combinations of x1 and x2, when we combine them, we just get r squared z to the minus 2. And that's looking more like what we might see in a book for the Z-transform tables. Then we need x1 plus x sub 2 now we're adding those. So the rz to the minus 1 can be factored out of both terms. And isn't it a good thing we're friends with Euler? Now Euler's screaming at us again. And that's just 2 of the cosines, right? So now we have 2r z to the minus 1 cosine of theta sub d. And that's the only pieces we need to find our answer. X of z was 1 minus 1/2 of their sum, and we just found that their sum involved a 2, so we now have those 2's canceling. That's now our numerator, and our denominator is 1 minus their sum, plus their product, R1 and or X sub 1 and X sub 2. And you might see that form, but you may see it in terms of positive exponents on z, but that's now the Z-transform of an exponentially damped cosine waveform. If we multiply that through top and bottom by 1, where 1 is now z squared over z squared, we get a z squared minus rz cosine of theta sub d. There's a common z in there, and we can factor that out. That's now our numerator, and our denominator becomes z squared minus 2r cosine theta sub dz plus r squared. And if we looked at the pole zero diagram in the complex plane, that's now just some combination of finite zeros and finite poles. We actually end up with in the z-plane I'll do the easy part. We get a 0 right at the origin. We also get a 0 at a distance over here of r cosine of theta sub d. But that's actually screaming at us too. A lot of screaming going on, isn't there? But this is now a distance of r. That's theta sub d, or omega sub d times our sample period. And in fact, our poles are complementary in the fact that if we have one above the real axis, we have one below at the same distance away, and we have this 0 right there, right below it. And this is now our pole zero diagram for an exponentially damped cosine waveform in the z-plane. It's pole and zero pattern. And you can compare that with what you had in the s-plane, and now in the z-plane, being over here in the right half plane isn't a bad thing, is it? As long as we're inside the unit circle, we're stable. So now we are how far away from the origin? We're a distance r, aren't we? And so as long as that r is less than 1, then we're in a good shape as far as our decay. But this could represent an exponentially growing if that r is outside the unit circle, and that transform is still valid. Because the region of convergence is for a value of z that's beyond that r. Questions on that? Let's then look at some properties of the Z-transform. And these are pretty much going to just be stated, although it might be pretty easy to sort of see what's happening sometimes rather quickly, so we may just walk through it. Linearity is preserved, meaning if somebody wanted the Z-transform of, let's say, one time domain waveform, f sub 1, and there, for whatever reason, I'm including the sample period in my argument for the time index. Then that Z-transform operation is a linear operation. The alphas are just constants, so they don't have to stay inside the Z-transform. I never know what scroll up or scroll down means, but is that what you wanted? I never know what's up or down. I guess that's scroll up, isn't it? I kind of think I've already been there, done that, so I need to go back or down. Never mind. Guess it's my time index. Are we okay with linearity? That means if we can identify, or if somebody gives us a sum of waveforms that we individually know their transform from a table, or we've derived it, we can then figure out what their combination is, a linear combination, by simply performing that same linear combination on their transforms. That's a nice thing. And I think one of your homework problems uses that, or you can apply that. Oh, can I keep going? I'm in a hurry. I don't know why, but oh, I know why. I want to cover a lot of material. Convolution. Everybody's friend, right? That still exists in the discrete time setting, which means now that if we take this particular combination so again, we flip and slide on the arguments. Now we are going to end up with, you know what? Didn't think I liked the looks of that. I'm summing over L. But if I take the time domain convolution of two waveforms, F sub 1 could represent my exciting waveform that's hitting my system. F sub 2 might be the unit pulse response of that system. Now if I convolve those in this way, I would get the, if I forgot this Z-transform, I would get the output response. But the Z-transform of that output response could be found by simply multiplying the transforms of those individual waveforms. Similar to what we've had in the time domain. Or I'm sorry, this is the time domain, in the continuous time setting. Another property. Time shift. Now we have to sort of know which is which. Let's say N is the time index, or that's the varying parameter. Maybe L is a fixed integer. Maybe we knew the Z-transform of f of n, and now somebody gives us a time-shifted version of that, depending on whether it's advanced or delayed. But L is whatever it is, a fixed integer. Then we simply can scale the original f of n's Z-transform, capital F of z, with this z operator, which z with a positive exponent is like an advance in the time domain. This is now z raised to the lth power, where we're advancing it L times. These could all be derived based on the definition of the Z-transform, but I'm not doing that. I'm just simply stating those. But this is similar to what happens when we let's say, delay in the time domain. We had an x of t minus tau. Then we have an e to the minus s tau, didn't we? And we know how z and e to the st are related between s and z. Another one. Let's look at, can't sneak out, can we? Give me a couple more years and you might be able to. Won't be able to hear you. I can't see you now, so you're fine. For visual, just if you come in early, oil the door and you've got it made, right? So now scaling in the, except when I see the oil can on the desk, that might give you away, right? I know what you're planning. Where was I? Oh, scaling. Not oiling, but oiler. Almost broke the Elmo. But oiler's our friend, right? So if you bring in an oil can, I'll be happy. It's spelled a little different, but I'll give you that, okay? What in the world? Oh, scaling. So now what happens if we scale? What if I now look at the Z-transform of r to the minus n f of n? That's actually f of rz. And what is this r to the minus n? That's just f of n divided by r to the n. So that's, if r is bigger than 1, then that's collapsing f of n quicker than f of n was collapsing on its own. And what's that doing? That's actually scaling the z variable in our Z-transform. So if you knew what f of n was, and somehow somebody has given you a new waveform, a g of n, that's related to f of n by a division of, let's say, r to the n, then you can compute g of z. That will just be f of rz. Capital F of rz. One more. Final value theorem. And this is useful because now if somebody says, oh, what's the limiting value of some signal? If you know it's Fourier or it's Z-transform, then you might be able to apply the final value theorem to see what the limiting value is. So here, if capital F of Z converges, for Z greater than 1, and all poles of a factor Z minus 1 scaling F of Z are inside the unit circle. If that's not true, then this thing's going to blow up and it's not going to go to anything. You could apply this limit and get a value that's not going to be right. So you need to make sure that these conditions are satisfied and not just apply the limit blindly. So now if capital F of Z converges and all the poles of Z minus 1 F of Z are inside the unit circle, then we can say the limit as time marches off to infinity, or limit as n goes to infinity of little f of n, is now going to be the limit as z goes to 1 of z minus 1 f of z, meaning you're hoping that there's some canceling going on. If not, then maybe your final value is indeed going to be 0. Maybe it's decaying, and so your final value is 0. Questions on those properties? Yes?
For this one, you have to check, the two conditions first. What is just do it?
So now you don't want to just apply this and then say, let me see if it's going to work. You want to make sure that so the question was, I think, can I just apply this limiting condition and then go back and check? You probably want to do it just the other way. You want to check that z minus 1 f of z has all of its poles inside the unit circle. If that's the case, then you can start looking at this limit. You can say my time domain limit of f of n as n goes to infinity is going to equal this limit as z goes to 1 of z minus 1 f of z. So you'll want to make sure that you are okay with the locations of your poles. Other questions? And you might want to go home and play with some examples. Look at some f of z's that you're comfortable with and see what happens when you apply this limit or this final value theorem. Now let's look at what happens when we want to find the frequency response. And now, just to give us something to sort of be thinking about, suppose we are given a system, h of z, which might be a filter, it might be a system. Suppose it is now 4 times z squared minus 2z z minus 1/4 factor times z minus 3/4 factor. And we can actually rewrite that numerator by factoring out a 4z. Is that system stable? If that's a system, where are your poles? Where are the poles? I might not be stable, but this guy is, isn't it? This transfer function. Are they in the right half plane or the left half plane, your poles? Right half plane. Does that mean anything? May or may not. Probably it's a good thing. Then you're not banging around so quickly. And you're on the real line, aren't you? Your poles are at 1/4 and 3/4. Those are both inside the unit circle. All you need is one bad boy to be outside the unit circle. You could have a transfer function that is maybe 25th order. On the exam, 12th order is probably as high as we'll go. Just be ready, okay? Drop ad forms are being signed after class. Where was I? Oh, signing drop ad forms. But before I do that, I forgot what I was trying to talk about now. But these are inside the unit disk, aren't they? And that's good. The right half plane is okay in the z plane. It's maybe better than the left half plane. Suppose now somebody excites this system with a waveform u of n of 5 cosine of pi over 4n. Do you see what that is in the time domain as a waveform? If this were my system that behaves like that capital H of z, now I'm shaking this sinusoidally, aren't I? And it's a linear system, so it's going to start shaking at the same frequency. After the transients die out, it's going to be vibrating or moving at the same frequency. I know I didn't get invited to halftime, but I should have, right? It's not being videoed that way, which is a good thing, right? This is a cosine waveform, just going up and down, but we're only seeing pieces of that, aren't we? This is now a 45-degree angle, meaning we're seeing this every 45 degrees. And some of those cosine may be 0. Some of those cosine might be 1, and it gets scaled by this amplitude of 5. We now want to know, okay, what's the output going to be when I'm shaking it in the sinusoidal steady state when I pass this signal, input signal, through that system? The system is stable. You told me that. So now the output should reach a steady state. And once it reaches a steady state, what frequency is it going to be oscillating at? The same omega sub dt that we hit it with, or that we're applying to it. So this is now, let's say, n greater than or equal to 0. We just keep hitting it with that. The picture that we have is something like that. And do you remember what we did in the Laplace setting, or for the continuous time case? How did we find the sinusoidal steady state response? Do you remember? What happened as your sinusoid went through that system? What did the system do to that sinusoid? Did it do one thing? Did it do two things? Did it do several things? Do you remember? If I'm shaking this system, what's possibly going to happen? We know it's going to shake at the same frequency, right? But will it be the same amplitude that we started with as the input? So the system may attenuate the amplitude, or it may make it bigger. That's going to be influenced by how this system behaves at that particular frequency of oscillation. And it may be what? Delayed a little bit. There may be a time shift. So we have an amplitude and a time shift that's going to happen to this cosine waveform that's getting applied to the system. Now we know our relationship between S and Z. I know you guys are still thinking about 12th order. But what do we know about Z and S? This could be a give me on the exam. Right? That's a unit advance. Or Z to the minus 1 is e to the minus S capital T, where T is our sample period. If we're interested in sinusoidal steady state, then we need to look at what's happening right along the imaginary axis in the S domain or the S plane. But if we replace S with j omega, now we have this e to the j omega t. And that's actually our frequency response for a discrete time system. This is now saying that we will replace z everywhere in our transfer function with e to the j omega t. If we sketch the picture, I should probably just draw it and then label it after the fact. That's our unit circle in the z-plane, and we know what h of z gave us. It gave us a 0 at the origin, gave us another 0 at 1/2, it gave us a pole at 1/4 and another pole at 3/4. And we can now put those on this z-plane sketch. We had a 0 and another 0, and then we had poles. And now what do we want? Well, now we want to walk around this stability boundary until we get to the frequency that we're interested in, the particular omega. And that omega t was actually equal to pi over 4 in this case. Our theta sub d was pi over 4. So we're actually walking up until we get right there. This is now z is equal to a magnitude of 1 at an angle of pi over 4, or e to the j pi over 4. And that's the point we need to evaluate our transfer function at. And we can do the same strategy that we applied in the S-plane. Now we can say, oh, if I have a factor z minus 3/4, I can figure out its contribution by finding the magnitude and the angle associated with that particular factor. Meaning I can go down here and I can measure that distance, that's the magnitude, and the angle, whatever that angle is between the positive real axis and that point z. I can do the same thing for these other singularities. Meaning I can now say that I have my frequency response for this particular example. I'm going to find along the stability boundary, and it's going to depend on what the theta sub d is, or the omega t actually is. And if I evaluate that, h of z, when z is equal to e to the j omega t, that's going to give me, in general, a complex number, isn't it? Because I'm now replacing all these z's with this complex exponential. And that's going to give me, and if you wanted to, you could apply Euler again and convert e to the j omega t to cosine omega t plus j sine omega t. If you wanted to do the rectangular decomposition of that particular point Z. If that's a complex number, then we can write it in not necessarily the rectangular form, but in the polar form as having a magnitude and an angle. Meaning we can find the magnitude. How do I want to write this? Now I need a bunch of vertical lines. And an angle. In our particular example, we had Z going to be e to the j theta sub d, where theta sub d was actually pi over 4. So now we evaluate h e to the j pi over 4, find its magnitude, and we find the angle of that complex number. And if I call this angle let's say phi, then my sinusoidal steady state output, y sub sinusoidal steady state of n, is going to be the original input's amplitude, which was 5, scaled by the magnitude of my transfer function at that particular frequency, and that's just going to be a number. If I take the magnitude of a complex number, h e to the j pi over 4 is just going to be a complex number. So if you had h of z on your calculator, you could say evaluate that at z equal to e to the j pi over 4, and it'll give you some complex number. Then find its absolute value or its magnitude, and that's what you'll put in right there. If you do that for this particular h, this actually ends up being about 4.9. Then we have the cosine. We continue to, if I'm shaking a system, and it's a linear system, and I'm shaking it at theta sub dn, it's going to end up, after the transients have died out, that's what this sinusoidal steady state means. After the transients have decayed, it's going to be shaking at the same frequency that I am exciting it at. But it may be delayed in time, and that's going to be this plus phi, where phi is that angle associated with h e to the j pi over 4. And in this particular example, in terms of degrees, and again, you would need to convert all of those to the same. Pi over 4 is in radians, so we have some radian value when we scale it by n, plus we'd need to convert minus 32 to a radian value before we took the cosine of that expression. But it's just usually convention, because we think maybe cleaner in angles than in radians, but that's the notation that we might use. Meaning we now have our sinusoidal steady state output is approximately 5 times 5, or 25, roughly, cosine of pi over 4n minus 32 degrees. And remember what we excited our system with? Our input was that, and our system, what What was that? Was that 4z, z minus 1/2? I don't know about you, but I'm impressed. That's now h of z. That's what we started with, I believe. So we excited this system with this cosine, and we end up with something that now has grown as it comes out of that system, and it's shifted a little bit in time by, what, a little bit less than a radian. What's a radian? 2 pi is 360, right? So you can divide 360 by 6, a little bit more than 6, so it's a little under 60 degrees, right? 57, I think, somewhere in there. Anyway. What have we done? We're now using the frequency response to find the sinusoidal steady-state response of a linear system. Let me just write that down. So we were using the frequency response, which we found that by marching around the boundary of our unit circle to a particular location, an angle, theta sub d, which was influenced by the frequency of the excitation source, using the frequency response to compute the sinusoidal steady-state response of a linear discrete time system excited by a sinusoidal input. So now if I give you a sine wave or a cosine wave, you need to find out what its angle is, that omega sub dt or the theta sub d. Then you can use that in your system's Ztransform. You can evaluate your system at e to the j theta sub d. That gives you a complex number. Once you have that complex number, you find its magnitude, and that's now how your original amplitude gets scaled, and you find the angle of that complex number, and that's how your waveform gets shifted in time relative to the original cosine waveform or sine waveform. So your system is shaking at exactly the same frequency that you excited it with. Its amplitude is either expanded or contracted based on the frequency response or what's happening. In this particular case, we are simply taking these lengths and dividing by the pole lengths, multiplying by, on the numerator, we have those lengths in the numerator multiplying each other, the denominators, and if we had a factor out front, which we did, I think it was 4, then we scale all of that by 4, and that's then the magnitude, which in this case ended up being 4.9. And we could look at all of these individual angles, and we have the angles of our zeros minus the angles of our poles, and that ends up giving us minus 32 in this particular problem. Questions on that? See a lot of blank stares. It's probably because I'm over time. So I appreciate you being patient. We'll pick up with region of convergence on Wednesday.